area of low pressure. Now, in the atmosphere, that warm, moist air rises. As it gets up in the atmosphere, it is robbed of its humidity. It moves north, as you can see, and then begins to cool as it moves north, and it sinks. So, the Hadley cell is composed of a belt of low pressure at the equator, and then secondly, a belt of high pressure at about 30 degrees north latitude. And that belt of high pressure at about 30 degrees north latitude is known as the subtropical highs. Sometimes we talk about the Bermuda high pressure, the Bermuda Azores high pressure. That's part of a belt of subtropical highs. So at the surface, we have a belt of lows, the intertropical convergence zone, and we have a belt of highs, the subtropical highs.
Next, we'll take a look at the polar cell. So we're going to go to the North Pole here. And because of the very cold air at the poles, the air is dense and therefore it sinks to the surface. And air sinking at the surface is high pressure. And of course, as always, air moves outward and clockwise away from high pressure. And so what that means is you get this northeast wind coming down from the poles, and that northeast wind then converges on the southwest wind, the westerlies coming up from the subtropical high pressure. So that area of convergence creates a belt of low pressure. Our first belt of low pressure was created because of heat at the equator. Our second belt of low pressure at about 50 to 60 degrees north and south latitude is created as winds converge on what is known as the polar front. And of course, convergence at the surface means uplift. So this is also an area where we have cloud showers and possibly thunderstorms. And the polar front really is the main location where most of our mid-latitude cyclones come from. And we'll talk about that in Chapter 8. The bottom line is the polar cell and the Hadley cell are both thermally driven convection cells, with cold air sinking at the North Pole driving the polar cell and warm air rising at the equator driving the Hadley cell. In between the two, the Ferrel cell, which goes in the opposite direction, is being mechanically driven by the rising, or the sinking air that is, at the subtropical highs and the rising air at the polar fronts. And so now we have the Hadley cell, the Ferrel cell, and the polar cell, and these different winds generating different parts of the globe in terms of climate. So at the subtropical belt of high pressure, sinking air creates a dry and a fair weather scenario. And at 30 degrees north latitude and 30 degrees south latitude, that is where you typically find the world's great deserts. In addition to that, of course, at the belt of low pressure known as the ITCZ, the Intertropical Convergence Zone, rising air creates showers and thunderstorms, and that's where you find the very wet and rainy regions, and along the equators where you can find the Amazon and the Congo. And then as you move south, 30 degrees south latitude is also where you find the world's deserts. And of course, the great desert of the world is going to be at the South Pole, Antarctica, where it's very, very cold, and sinking air keeps the weather generally dry. We don't get a lot of precipitation there, and it's one of the world's great deserts. Other factors within the three-cell model, we have the horse latitudes and the doldrums. The horse latitudes at that subtropical high where the wind's very light, so old-time sailing ships would be becalmed. They would not be able to make much headway because of a lack of wind. And then the doldrums down at the equator, where weather conditions are essentially the same all of the time, hot, humid, and stormy, so there's not a whole lot of change. And again, this three-cell model dictates the general climate features that we find around the globe.
Let's now talk about how that global atmospheric circulation affects our surface winds. And one of the first things you need to understand, because the northern hemisphere has so much land, and we know that land and water heat up and cool off differently, it does create some fluctuations in some of these wind patterns. The first one being the ITCZ shifts with the seasons, meaning in the summer seasons, as you can see on the left-hand side in this illustration, that thermal low over the Tibetan Plateau pulls the ITCZ well to the north. And even the thermal low over the southwest desert of the continental United States pulls the ITCZ a little bit further to the north. So you can see that ITCZ is a little north of the equator in the summertime. In the wintertime, it drops back down toward the equator, but you can also see where it's pulled further south of the equator, where the Australian thermal low will develop, and even over Africa and over South America, pulls that ITC to the south. Now, one of the big prevailing pressure patterns that creates a lot of the wind that we deal with is going to be those subtropical highs. So let's look at the summertime first on the the wintertime, excuse me, first on the right, where you have almost a continuous stream of those subtropical highs. The Pacific, the Bermuda, even the Siberian and the Canadian high are near the subtropics, and those high pressure cells create these constant clockwise turning of winds, bringing us the trade winds in the lower latitudes, and then also the westerly winds in the upper latitudes. In the summertime, we do get that thermal low over Asia and that thermal low over the southwestern desert, and that changes the patterns just a little bit. But you can see that Bermuda high pressure, whether it's shifted a little bit to the west in the summer or back to the east in the winter, is very significant in bringing that hot, muggy weather to the eastern United States. So how does the general circulation of the atmosphere affect the general precipitation patterns of the globe? And if you watch that YouTube video from 2 slides ago, you'd have some idea. But look at this illustration on the right. You have the globe. You have your ITCZ in the equatorial zone, those lows, that belt of low pressure along the equator. And of course, that produces hot, humid, and rainy conditions. And so over Africa, you have the Congo region, and over South America, you have the Amazon region. And then if you go north in the northern hemisphere, that belt at 30 degrees, the subtropical high, that's where you get sub-Saharan Africa and the Middle East, and even the deserts and the desertification of Asia, including parts of India. And that is, again, because of sinking air at the subtropical high. High pressure, fair weather, very little rainfall. And then once you get up to about 50 to 60 degrees, you start getting those subpolar lows, that polar front, and once again you get showery, rainy weather. And that's where you get the more temperate zones and the wet weather of Europe and northern parts of Asia and including places like Russia, but also in the continental United States. We have the wetter regions of the continental U.S. and up into Canada. And then, of course, at the polar regions, once again, that's high pressure, fair weather. So really the world's greatest deserts are at the poles, where there's very, very little precipitation because of that high pressure. And we can see in this illustration to the left where our Bermuda high and our Pacific high help to create nice, warm, humid air across the southeast, but much cooler and drier air across the west coast of the United States. Now, in terms of the global circulation of the atmosphere and the larger scale, the global scale, now we're talking about the westerlies in the upper levels of the atmosphere. So now we're beginning to talk about not the westerlies at the surface, but the westerlies in the upper levels are jet stream. So the jet stream is a relatively narrow band of strong wind in the upper levels of the atmosphere. The winds blow from west to east in the jet stream, often shifting a little bit north and south, meaning jet stream winds can be almost due west to east. We call that zonal, but very oftentimes they get wavy and they dip north and they dip south and pull north, and that's called meridional, but generally the flow is from west to east. And these jet streams literally follow boundaries in the atmosphere between hot air and cold air. Since these hot air and cold air boundaries are most pronounced in the wintertime, jet streams are typically strongest in the wintertime. And you can see where the looping pattern of that polar jet oftentimes plays a very important role in global heat transport, as it does move cold air from north to south. That's how we get our cold air in the wintertime here in Florida. The jet stream dips nice and far south and brings a blast of cold air for a day or two, but also pulls warm air south to north as well. Not only is there a polar jet or a polar jet stream, there's also a subtropical jet that's not always there. It's more intermittent, but largely it is in place. But I also want to point out that the illustration shows these as almost continuous rivers of air. Sometimes these rivers are broken down in terms of their speeds, with faster areas in some spots called jet streaks and slower areas in other locations. These are the illustrations as to why the jet streams occur and how they occur. So the subtropical jets typically located about 30 degrees latitude just on the poleward side of the Hadley cell, and the polar front jet is located between 50 and 60 degrees latitude on the poleward side of that Ferrel cell. So I want to start out with this illustration on the right. If you look at this, we'll start at the equator to the far right. That's where we have that belt of low pressure. That's where the air is warmest at the equator. And so what happens to the atmosphere? It is thickest. The atmosphere from the surface to the top of the troposphere to the tropopause. So just imagine that kind of that shaded purple surface you see at the top of the illustration being the tropopause. The atmosphere is thickest where it's warmest at the equator, and then it gets thinner as you get poleward where the weather is colder. So that transition zone between the warm air and the cold air is going to be that 30 degrees north latitude. And what happens to warm air as it moves toward the cold air, as that high pressure aloft moves toward that low pressure aloft? Well, yes, the wind turns to the right because of Coriolis. So we start out moving north, it turns to the right because of Coriolis, and the difference between that warm air and cold air creating that subtropical jet. Now, between 30 and about 50 to 60 degrees north latitude, there again, you have a very big difference between warmer or say moderate air over the mid-latitudes and the colder polar air. And that once again creates the jet stream, and the deflection to the right creates the polar jet. You can see a very similar illustration of this to the left, where we have the cold air to the north, the warm air to the south, the thicker atmosphere to the south, the thinner atmosphere to the north, and that movement of air from the warmer to the colder and turning right because of Coriolis, creating those stronger winds in the upper levels of the atmosphere. At the global scale, these larger scale wind patterns also affect the oceans and create our ocean currents. So as wind blows over the ocean, it causes the surface of the water to be dragged along with it. And that surface being dragged along with the wind because of friction pulls water at deeper and deeper levels along with it. So in this way, the general wind flow around the globe starts the major ocean currents moving. Higher friction of the water means that it's not going to move as quickly as the wind. So the wind may be blowing at 15 or 20 miles per hour, and the water underlying that wind may only blow at 2 to 5 to 6 or 8 miles per hour. But in this way, with those belts of high pressure at the 30 degrees north and 30 degrees south lines, those belts of high pressure, whether they're Bermuda Azores high to the north in the North Atlantic or the Pacific high in the North Pacific, the clockwise flow around those belts of high pressure, both northern hemisphere and southern hemisphere. Of course, in the southern hemisphere, it's a counterclockwise flow around high pressure. Those high pressure cells and the winds around high pressure cause the ocean currents to loop as well. And those loops are almost closed, not quite closed. Ocean currents that loop in the major ocean basins, North Atlantic, North Pacific, South Atlantic, and the Indian Ocean, those loops are called gyres, G-Y-R-E-S. So on the eastern edge of continents, the eastern edge of the continent, like here on the east coast of the United States, poleward moving currents move warm water to higher latitudes like the Gulf Stream, and in the Pacific the Kuroshio Current. On the western sides of continents, equatorward moving currents move cold or cool water to the lower latitudes. That's like the California Current, or on the west side of Africa, the Bengal currents. That's where cold water is moved toward the equator. 40% of the total heat transport in the northern hemisphere occurs because of ocean currents. It's higher in the southern hemisphere because there's just more water down there. This is what those ocean currents look like, with the North Atlantic Current and the Gulf Stream taking warm air north. And understand the dramatic impact of this. Look at where the Western Europe is, whether it's France or the UK, at the latitude it exists. Take that straight across the west to Canada, and you can see that that's like central and northern Canada, very frigidly cold areas of Canada. The reason why Western Europe is not nearly as cold as a climate is because that Gulf Stream pulls a tremendous amount of warm water toward Western Europe. Similar situation, why is it always so cold in the water in California?